Welcome back. Welcome back to the Varia track, the best track to be at this conference, and where we discuss different elements related to our data ecosystem. I hope everyone is sitting comfortably. Everyone has a proper drink because we still have two very interesting talks ahead of us. And the first one, it is my pleasure to introduce Dr. Tim Frey, who's the managing director at Unera. Dr. Tim will answer the question whether the changing realities of our life are the final frontier for machine learning. Tim, the floor is yours.
Okay, thank you everyone for having me here. And I'm glad that I'm here at the second online edition. And I hope that next year we see us again in person. So let me talk about adaptive AI. So it always is a nice and fancy topic to talk about, but what does it mean? What are changing realities, and is it really a problem for machine learning? So I would like to guide you through, let's say, our journey that we had by finding changing realities in a specific use case, and then I would like to talk with you how we overcame these changing realities. But first of all, let's do a quick intro about me. So, who am I? What do I do? And what's my life for? So, I'm a software engineer by heart. So, I like building software, constructing software, doing the architecture. Um, I think, regardless how many things I manage, I will always love doing that. And I believe that only great software can deliver big data scenarios as a service. And the key problems that I have in my life is always to acquire data and valuable data and clean data. And therefore, I'm a data marketplace enthusiast because what still is the thing, even if there are changing realities making my life difficult, it's the bigger problem always to get the data that you need. And I believe that big data can, in special the changing realities thing, can have a big impact for sustainability of our globe. And that is also related to our use case that I will present you in public transport. And there we can improve that. So that is me. That is what my life is about. That is my background. So let's talk about the use case. So when we have public transport, let's imagine that we have different lines and the lines depart at different hours. So the y-axis are the lines, the x-axis are the hours during the day. And what we see there is that the darker the color, the more occupied some vehicle is. So as simple as that. So what we see here is that the lines do not have the same occupancy during and daytime. So the, let's say, the rush hours of the lines are differing. And that is the already first question: how do we build machine learning models for that? But let's make that a little bit more complicated. We have here now the complete occupation of all lines of a public transport provider, and we colored that nicely in weekdays, weekends, school days, and so on and so forth. And the thing is, where you see the red circles, that is where lockdowns in that area were happening due to corona. And the question is, when we see that before, it's data from 2018 going up to 2019 and 20, then the question is, are these patterns then re-emerging or just to a smaller scale emerging that there were before? So can we still predict how full it will be, or can't we do that? So what would we do with a traditional machine learning approach when we think about, when we do not consider some things like corona? We would go there, we would take some old data, we would search the right algorithm, try to build a prediction model, maybe one prediction model for the whole public transport, and say the line is then a feature or so. And ultimately, we will use the training data, and then we would evaluate and deploy all of our great forecasting models to production. Most likely, we would already find a few flaws called seasons. called weekdays, called weekends, called school, it's called fairs, fairs where a lot of people visit the city, or Christmas markets or whatsoever. And they would disrupt our model. Okay, we might say, okay, it does not always work, and there are some occasions where it does not work anymore. It's just is working through normal weekdays, and this special occasions like fairs or school holidays do not matter to us. We still would deploy it, and then we have a very nice, let's say, forecasting solution. When we look at that, we could even feed the daytime, and I want to show you how different, even in that, without Corona, um, a normal weekday is from a weekend. So we have a Monday, there we have a clear rush hour, again, complete data of one public transport, that the lines have different rush hours is now kept aside, and we see now very nice. From 7 to 8, we have a peak, and then the people at 13 to 1400, there is a peak again. So then we have a Saturday in comparison. So first of all, we shift the peak hour from 7 to 8, from 8 to 9. And there is no peak at noon anymore. It's quite logical, it's a weekend. And the magnitude that I think that was factor 20 or so lesser. So even that the lines see similar height, it's not similar height at all, that at the weekend, the public transport is so empty compared to the week. This is a smaller town, a smaller city town. Might not be completely count for densely populated areas like London, Berlin, and Munich, and so on. But here we see that there is a significant difference. And even in Berlin and so on, it would be totally different for the workforce. So how would we solve that thing? So we take the training data, then we take some seasonal trend overlay data, weekend weather data, maybe weekdays, and then we push that into our REMA models, and then or exponential smoothing or a short-term, long-term memory, and try to forecast. Thing is, let's look at the Corona thing, because that is we still can talk about weekdays, weekends, and seasons, but we cannot speak about things like Corona. So that's a really nice picture. That's the London data, and there are two things interesting. One is that the majority of the transport and the kilometers per year shifting passengers is not the underground, it's the buses. So buses matter for climate change, even that it does not sound fancy, even that all people talk about rail, buses matter. They are the main means of public transport. When you go to countries like India and so on, that is moving billions of people, then buses matter even more than trains. So when we want to improve something in our world, then we need to improve buses. It's unsexy, but it's true. But we see how it was hitting the impact of Corona was hitting the London transport. It totally crashes down. So in any case, when we now would feed that into a traditional model, it would not work. So in addition to that, public transport does, in Germany at least, not have great amounts of data. We are talking about, I would say, 10 to 20% of all occupancy data is available. So, and partially the people counting systems are rotated between lines. So you see there down people counted data. And what happens quite often is that there are gaps in the data. You don't have data for a few days. That's normal. Maybe the bus is broken. Maybe the bus is on another line. So you do not know what's happening there. The second thing is you have what you have seen in this London example. You have nonlinear changes due to some fact of impact of a sudden event like Corona. But you also have that normally that out of some strange things, there is school holidays ending, and then exactly that is happening. And what I said before, data holes, that's a huge thing, that you seem not to have always all data of one line. So it can be that you might have 60% of a line, and then they took the people counter on a counting bus on another line, and the other, yeah, because the people counting systems are installed to credit the revenue distribution in public transport. So they might just move it from line to line. So, and it was never used or planned to be used for predictions. So you have the data holes naturally, and then you have some technical difficulties, like maybe the upload is not working or so, and then there's the data missing. Last but not least, even that I talk about big data, you have a data quantity problem, because you do not have enough data to a significant time back into the past. There's one. And second, the past is changing. When we think about, we want a large data quantity today and model the public transport out post-corona, then we have cheaper tickets in Germany. We have special offerings like a line Euro ticket. So, and you do not have on a sudden significant data to train a model. So that means you need to learn very quickly from a small amount of data. So the quantity for that, what you want to learn from, and to extrapolate what you can predict, is very often not there in that amount what you want to have. Last but not least, there are counting errors and data corrections that you need, but let's not get into that. But it's a very effortful topic. What I want to get in is, what does this mean for our machine learning deployments? Maybe the algorithm that you wanted to use to predict does not work anymore. I mean, we are talking about the thing that we trained an algorithm, and the algorithm was able to make a prediction in the past, but maybe the algorithm is wrong, so we cannot use the same algorithm in the future. And in addition, the model is changing for sure, so we have a double change that is a double effort. This just train once and then deploy and it works forever. This is not working in that case, and that is over. So when we are talking about that data is changing, that might imply that the prediction models are not working anymore. And that means that we cannot have our normal value chain where we train a model, push it in some repository, and then it's uploaded automatically. No, we need to retrain that often, that we need to solve that differently. So changing reality mean huge problems for machine learning. Let's get away a bit from public transport. The generalized problem is that when you have something that is called concept drift, when you want to look it up about scientific publications. So there are concept drifts, and the question of what to do with concept drifts. So another problem that we have here like that is, you have a smartphone and you try to say, what is the predicted idle temperature or so? And when you would try to predict it, it would be totally different from summer to winter. And when you then go into an airplane and you come out of an airplane in Oman or so, and it's in the winter hot there, then the idle temperature would be hot, even that your smartphone is a European smartphone. So that are concept drifts that happen often slowly, but they can also happen in a sudden, like the weather change when you go through an airplane, and so on. In enterprise systems and data warehousing, that is called slowly changing dimensions. That could be that a store manager changes and you try to do predictions of the sales of a store, and the store manager changed. It's another store manager, so there is another master data, speaking in the traditional data warehousing sense, that could totally have an impact on the sales of the store. And you would need to respect that as feature in machine learning. So that are the things that need to consider. Inflation, when you predict prices and so on, typical thing of machine learning where that counts. Car sales forecast, when we talk about e-fuels, when we talk about electric cars in general, when we talk about subventions for the cars, that has a lot of impact on the car sales. So it's not just the thing in public transport. It can go in every area. Bull market, bear market on the stock. Yeah, that the perception publicly of something has changed. Like we have that example now at the World Championship and so on. What is the perception? Maybe people do not buy products from a country anymore when it's not perceived so well, and so on and so forth. And ultimately, in all sensor-based things, all the weather stuff and conditions, and when you would deploy machines and you would measure their their temperature and so on, the machine is deployed in another country, then it changes. And ultimately, when you are running your online store and you forget that there is Christmas and you have a forecasting model for purchasing goods that you want to sell each month, there is Christmas, then you will miss out on a lot of revenues when you do not consider that the forecast of your sales could be very, very different on Christmas. Yeah, and then there's the slow change of global warming. What does that mean when you have the concept drifts and you do forecasting? At the bottom, you see an adaptive model that can handle concept drifts that we built. And there, the adaptive model has the first two peaks. The pink one is the forecast, the blue one is the reality. And you see on day 3, it started to adjust itself for the amount of passengers. And when you look up, there we have a regularly deviation of the, let's say, actual occupancy towards the pink prediction, because the people bounced back faster than expected. The model was trained for a lesser amount, so there is a deviation. The interesting thing is, in the up picture, the top picture, you see that we still can say when the peaks happen. So that is, in fact, when we did our attempts, that top picture was the first one that we generated, where we saw, okay, in general, the patterns are still there. They are just there in a different magnitude and a little bit shifted. So that's the thing. What happens when concept drifts hit you? You just are not striking any bullets anymore, and putting the right predictions. The solution one, that it ultimately not work for us for that case. But it would be that you use online learning tools that adjust models, and that you split data stream into training and forecasting. You continuously train models, and then use always the newest model, and you train multiple algorithms at the same time, and you monitor the models and you retrain them. We used that very successfully for predicting cryptocurrencies in the past. There it worked very well. For that attempt, it did not work, but I want to show it to you anyway, because it's one solution that could generally work for such changing realities. So what you can do is, how can you do online learning? You can say, okay, I have a number of features, and I say, what is the occupancy before a bus stop and after a bus stop? And then I take all of the features and I have a historical situation. That line with that amount of people already in there then led to a situation afterwards, after the bus stop. And I can use that as training data. So, and I use this situation led to this situation. I take that as record and I feed it into my model. So, and I'm one step back behind the current reality. And once the current reality happened, I take that set of the current reality and feed it into the model as well. So, but now the current reality happens, so we use that for prediction. How does that work? So we have all that record sets of that situation led to that outcome, and we feed each of the record sets into different models. Then we evaluate based on the present situation that we have. So we take a new situation that is flowing in. Now the bus stopped. We have a new record set. Then we take that and we said, could it have been able to predict this record set? So we will evaluate the model continuously. Out of that, we get a data stream out of evaluation. Each time bus stops, we have a new set which algorithm still worked. After we evaluated it, we feed it into the model and say, okay, learn from that record set. So, but we know now one step in the past, how well would this algorithm have been able to predict the future? So we currently can compare always if it worked or if it didn't. From that, we do statistical collection, analysis, monitoring, and say this model is healthy and which model is working for predictions. Then we determine out of these numbers which model is currently working best. And then we have the ignition to say that is our current algorithm. And after each training, we look at the statistics if the algorithm is still fine. That are the newest scientific algorithms that they have from universities. They are not very stable. They are not so nicely documented. You have to read a lot of papers when you use, in special when they use the Apache MOA library. Really great. I recommend that, but it might not be completely industry ready. Key problem that we had were the data holes in this thing. We did not overcome the data holes, that there was just data missing. And it was not working with the rapid adjustment times. Maybe that could have been solved, but in combination with the data holes, it was the overkill. And the third thing was the feature importance changed. We recognized in public transport the feature importance of line and so on changed. Strangely, I do not understand why it changed, but it changed, and the models were not able to adjust to that. Why? But let's say we're not able to adjust to that so fast. But all of that might work for, let's say we even applied it for other cases, and there it worked. So strategy 2, nicer, easier, but takes more engineering effort, adaptive calibration features, how we call it. Adaptive calibration features are, you identify, first of all, the unpredictable events. So you say it could go wrong. There might be something that is unpredictable, like the passengers drop down. And what could this event be? What is the event? Then you think about which features could be related to this unpredictable event. And then ultimately, which features could have an impact on the changing value, so on the occupancy, and which features that might have a relation to this changing value might relate over time. So is there a feature that you can say before a lockdown, before this unpredictable event that you say there is a passenger drop, could relate to the past and the present? So in short, let's imagine the daily complete occupation of all. So you can say, I had the daily occupation of today, and I had the daily occupation of 2 weeks ago, and I can compare them. And I could feed such a feature into my machine learning model. And if I did the right thoughts, these features will implicitly show that there was some lockdown. So then we made a long list of features, amount of passengers change, last weekend, and we thought about a lot of them, and we rated them in dependent and independent. So dependent features is last week and yesterday. So that is a dependent feature. It's a time feature. It's completely dependent on another. When we say amount of passengers yesterday or 1 week ago and 2 weeks ago, that's completely dependent on another. That's not orthogonal. It's just expressed the same thing in a different way. And we first should check if it works with 1 week ago before we check 1 week, one day, 5 days, 7 days. It does not make sense. We first need to see if the feature generally works. And that is exactly what we did. So, and then we trained our models and saw and rated then the importance of the features. We checked which feature is how relevant for the forecast, and then we made it more fine-grained in, say, 5 days ago or 2 days ago, and so on. So how is the outcome of that? You have here an independent feature can also be normalization, that you say you normalize the people, because we realized that there are very often empty buses even before Corona. So, and when it's full, then it's more full. So it's not so important if there are 5 people more or 5 people less. We can just focus on a normalization that to make it more linear. So we found models to mathematically smoothen and, let's say, normalize the amount of people in a bus. And that helped a lot how many go in and out. And there are stops like a school. A lot of pupils go out of the school. So we want to, let's say, normalize the amount of people getting out of the bus. And then we found out that percentage to total works very well. And ultimately, we found out that a weekday was not so important after all. We thought the whole time the weekday is important, but you need to be honest with yourself when you do that. You need to try the features and then to let some evaluation tools rate your features and see which features really have an impact. And that was there, the percentage to current total. So how many people were yesterday and what's the percentage to the current total. So, and with that, you then work out which features you feed. And then you can train the model more or less normally. And the past value comparison, what I explained now right now, is the key thing. The problem about these approaches and why I never liked it, even that it worked, is that it's a lot of engineering effort. And I like engineering solutions that are adaptive by pure software without human interaction. And when there are new other unpredictable events, this might break down when you have different circumstances. And when you have an engineering solution that is just adaptive, that works. But the data halls made it impossible to apply the other approach. So that worked well. That is what I can give you as a guideline there. So what do changing realities do to machine learning? Basically, you look them up as concept drifts, and it's changes of the real world that are reflected in data, and they mess up your models. And they render your models in worst cases useless, and you're not so able uh, to to be predictive so well anymore. So whatever you do, concept drifts can happen. Monitor your models. It's not enough to deploy a machine learning model. Even in normal cases, very often the reality drifts. So model monitoring is, in my opinion, a total underestimated part of machine learning that should be considered much more, because once you have the model in production, you need to define what happens if it's not predictive anymore. What do we define? Not we retrain it each week or so. When it's really crucial for your business, like forecasting sales or so, you should define how predictive the model needs to be, and you need to monitor it, and you define what happens if you can't predict anymore. What are the implications when you engineer features when there are concept drifts? You can do the first solution. What I proposed, that is, you update the models continuously, and you train multiple algorithms, and then you have a big statistic collection and so on. That is resource intense. You can imagine when you train 20 algorithms, like we did in another case once, then you train 20 algorithms, and we had a model for each line. So that can be resource intense, even if you don't use things like neural networks and so on. So that is the downside there. Or you invest the time and find features that reflect the changes in the prediction that can be used to adjust the outcome of your predictions. That is ultimately engineering intense. So that's good for our job. So both of them are a very good thing, that not everything is done, and there is so much more that we can do in the future. With that, I would like to thank you for listening, and I'm curious for your questions.
Thank you very much, team. Tim, very, very interesting presentation about, I think, the true nature of actually machine learning, right? Because our world is changing all the time, and we should be looking for ways uh, to automate, but within kind of sensible realm. And my question here is, how much really we can automate of the entire kind of machine learning pipeline? Because from your presentation, it is still obvious that we need human in the loop for many different reasons. And if you could maybe say which parts could sensibly and comfortably be just purely machine learning tasks, and where human intervention is just critical today.
I think it's monitoring. It sounds strange, but I think the really core thing is monitoring, because the models they often run out of hands. You we are currently thinking, we design a model, then we deploy it. That's the business viewpoint, and then we deploy it. But I come from a software engineering craft. When you build a software product, you need the same amount of people to maintain the product, to increment the product, like you need to develop the product. And in machine learning, the people are thinking, you develop the model and then you deploy it and then it's good. No, you need then ultimately a team handling the monitoring and the updating of the current approach. And I think that is the key thing that can never be outsourced. I think you can automate the training of models with resources. You can say, okay, I train every algorithm on the cluster. I try all combinations. You can do that with money. But what you cannot do with money is to evaluate the outcome. At least that's my viewpoint there.
Okay, and I think the issue is specifically for the non-technical crowd within the organization is the name itself, machine learning, right? People think that they just learn by themselves. It's exactly what you said. Once you put them on production, it's machine is learning. You don't have to do anything. So it might be even the name of this that is a bit misleading. We have one question from Tevfik. He's asking how frequently models on production should be monitored.
Well, I think that's use case specific. So uh, I think there should be for sure alerting. So what I would always do in production is to have alert parameters where you look at it. So that is that you say, if my model fails one day completely, that's not so bad like if it is not accurately one day. So that you have, when you have a drop in predictability one day, then you need to say, okay, I monitor it instantly. So that's kind of anomaly detection of predictiveness. And the second thing is, it depends heavily on the use case. When you have something like inflation, and you would, you predict financial markets, and there is inflation in, and there is a big concept drift, and your concept drift is known already, then you may tie it to that you say there is a parameter, or like seasons and so on. When you have really a machine deployed in Germany, and there are seasons, then you should look at it at the winter. So you should always look at what can have an impact. But at least once a month, I think a model should be checked how good it was.
Mhm. Okay.
But I think these escalation things are important to have that as addition. But I think you can't never deploy something and not look at it.
Yeah. Yeah. Sounds just like a reasonable rule of thumb. Um, so another question is from Orsalia, and she says, it was a bit fast for me to fully follow the presentations where the two solutions for data drift here envisioned for time series models. Or it does it only apply to time series models, or this applies to any machine learning applications? And then the question that follows, which were the underlying methodologies in the use cases presented?
Okay, I can answer. So in theory, I only focus on time series. Okay, that's what I do with my life. So that is that is, let's say, the disclaimer before I answer that question. Yeah. So what I know is that time series can even happen for image recognition, because yeah, or sound recognition, or even that it changes over time. So in theory, but there it's much slower, so it's not so important. Then you might have a new job already and the application is still running, so don't care about that. That image shifts, at least of what I read of them, where some people prove the time series happen, concept drifts happen everywhere, even with images. uh, that's so long time that this happens. I think that does not matter. um, so mainly for time series is my viewpoint. But without my disclaimer on top that this is my own focus. Um, the underlying methodologies were, we made continuous retraining, or we trained the algorithm continuously. Some machine learning libraries can do that. That was the first use case, more or less. That did not work. There we trained the algorithm all the time again, and each new data set that was there, we pushed it into the algorithm. That was methodology one. That did not work, mainly because there were data holes in our use case. And for that data holes, we came up with features, with features that we fed into machine learning that were reflecting the concept drift. So we said, okay, if the passengers drop from 1 week to another and the percentage is down by 30%, and we feed that in how many people are in relation to last week in the bus, then we have something that can that our model can use to adjust the output of the model. But the problem is to find something that reflects that reality change in your data without having an external event list or something like that. You need it really from the data. You need to come up with a feature that is in the data itself already visible, and you just can express the time relation in the data.
Mhm.
And now I hope that is better understandable, but you are also invited to email me or so. That's all fine, because I know that it's hard to understand that.
Okay, good. Thank you very much, Tim. It was a very interesting introduction to these concepts, and yes, stay along. Thank you for the presentation, and for everyone, please stay on the in our track, because we still have one presentation ahead of us about the legal aspects of the European data strategy. Thank you very much, Tim.
Okay, thank you. Thank you for having me, Pavel. Have a great time. Bye.
Bye.